Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 4. In this lecture, we'll discuss energy of the mass spring system and a simple harmonic motion. These topics are covered in Chapter 15 of our textbook by Surway and Jouet. Let's begin with a review of what we've been doing over the last few lectures. We're interested in studying the behavior of a simple mass spring system. We'll study more complicated systems later, but it's essential that we have a thorough understanding of the simple mass spring system before we can bring in other forces like friction or a driving force. We decided that for a simple mass spring system, the behavior is described by this equation here. This is a second-order differential equation which basically tells us how the position of a mass changes as a function of time. We obtained this differential equation by combining Newton's second law of motion and Hooke's law for the spring force. Based on our knowledge of calculus and derivatives, we found that the solution to this differential equation is this function here. Of course, this function can be written in other forms. For example, you could add 2 pi to the argument of this function, or you could add pi to the argument and multiply the entire function by a negative sign, or even write the cosine as a sine function. Those are all equivalent forms of the same thing. However, by convention, we're going to use this form of the solution. This function has 3 important parameters: a, which is known as amplitude, omega, which is known as angular frequency, and phi, which is known as phase constant. Omega is easy to calculate. It is the square root of the spring constant divided by mass. A and phi can be a little more challenging to compute. They depend on the initial conditions of the system. More specifically, they depend on the initial position of the object at t equals 0 and its initial velocity. Note that once you have obtained the position as a function of time, you can now calculate a lot of other useful quantities about the mass spring system. For example, you can take the derivative of this function and find the velocity as a function of time. You can also take another derivative and find acceleration as a function of time. For the next couple of slides, our goal will be to study the energy of the mass spring system, starting with this equation here. We're interested in calculating the energy of a simple mass spring system. More specifically, we're interested in calculating the mechanical energy of the mass spring system. Recall that mechanical energy is defined as kinetic energy plus potential energy. For now, we're talking about a mass spring system that oscillates horizontally, so we're going to assume that there is no gravitational potential energy, there's only spring potential energy. Hopefully from your mechanics course, you remember that kinetic energy can be calculated by 1/2 mv squared, and that spring potential energy can be calculated by 1/2 kx squared. We have found an expression for the position of a mass as it oscillates, so we should be able to calculate the spring potential energy by substituting that expression in here. By differentiating that expression, we should be able to find the velocity of the mass, and we should be able to substitute that in here. We know that position changes as a function of time, so we suspect that velocity must change as a function of time, and therefore mechanical energy could change as a function of time. So our goal now is to find mechanical energy as a function of time. We would like to know what the mechanical energy of the system is at any given time. To begin with, recall that the position of the mass as a function of time is equal to a cosine omega t plus phi. You're going to have to figure out what a, omega, and phi are, either based on a description of the problem or a graph that is given to you. For now, we'll just assume that you've already done all that work and that you know exactly what a, omega, and phi are. If you know what those parameters are, then you can take a derivative of this function and find the velocity as a function of time. Remember, velocity is the derivative of position with respect to time. Hopefully you remember from your calculus class that the derivative of cosine is minus sine, and of course you have to take the derivative of the argument, so we'll take the derivative of omega t plus phi with respect to t, which gives us omega. Now that we have the velocity and the position as functions of time, we can take these two functions and plug them in for x here and v here and find the mechanical energy of the system. When we do that, this is what we get. For kinetic energy, we get 1/2 m, and then this entire thing is velocity. We're going to have to square it. For spring potential energy, we get 1/2 k, and then this entire expression inside the square brackets is x, and we'll square that. Now, this initially looks like a very complicated expression, but we can simplify it a little bit. For example, note that the minus sign here goes away because we're squaring it. So we'll end up with 1/2 m omega squared a squared sine squared. That's the spring potential energy. Sorry, that's the kinetic energy. And then for the spring potential energy, we get 1/2 k a squared times cosine squared. Now, this still looks like a complicated expression until you recall that omega is actually equal to the square root of k over m. So this omega here, which is squared, can be written as k over m. When you do that, things simplify considerably because now what we have is omega squared, which is going to be equal to k over m, and this m will cancel each other out, so we'll end up with 1/2 k a squared. 1/2 k squared also shows up here, so we can factor it out, and what we'll end up with is 1/2 k a squared times sine squared plus cosine squared. Now, hopefully you remember from your trigonometry class that sine squared plus cosine squared is equal to 1, and so this whole long, complicated expression actually simplifies to a very nice, simple expression. We find that the mechanical energy of the mass spring system is simply 1/2 k a squared. Remember that k is the spring constant. It's the thing that tells you how stiff the spring is. And a is the amplitude. It is the maximum displacement of the mass from its equilibrium value. Notice that this expression does not depend on time. K is a constant and a is a constant. So what our calculation shows here is that the mechanical energy is constant, and that constant is equal to 1/2 k a squared. Another way of saying the same thing is to say that mechanical energy is conserved. The kinetic energy changes as a function of time, the potential energy changes as a function of time, but those two, in a sense, are engaged in a seesaw action. As one of them goes up, the other one comes down, so that the sum of those two types of energy ends up being conserved or constant. This shouldn't be surprising. After all, we're talking about a simple mass spring system. We're assuming there's no friction, there's no resistive forces, so we expected the energy to be conserved, but it's nice to be able to prove that fact, and it's nice to be able to calculate that conserved energy. Let's do a practice problem involving energy. A block with a mass of 2 kilograms is connected to a spring with a force constant of 10 newtons per meter. At t equals 0, the block is pulled a distance of 0.5 meters from equilibrium and then released. Calculate the block's speed at x equals 0.3 meters. So the block initially starts at 0.5 meters. Its initial velocity is 0 because we're not giving it a push, we're simply releasing it from rest. But of course, as soon as we release it, there is a force acting on it, so the block begins to accelerate, and it goes faster and faster and faster. It goes from 0.5 meters to 0.4 meters to 0.3 meters. It's moving towards its equilibrium position, and as it does so, it builds speed. We'd like to know exactly what its speed is when it reaches x equals 0.3 meters. Now, it turns out there are two ways to answer this question. The more difficult way to answer this question is to start by saying that the position as a function of time is equal to a cosine omega t plus phi, and then take a derivative of this expression to find velocity as a function of time, and that will end up being minus omega a sine of omega t plus phi. Now, in principle, we can use this expression to calculate the block's speed. However, in practice, this is a very difficult way to solve this problem simply because we need to figure out what A is, we need to figure out what omega is, we need to figure out what phi is, and we also need to figure out what time is. Notice we're not told at what time the block is located here. We're given the position of the block, but we're not given the time. So in principle, we can calculate all that stuff and then plug it into this expression here and calculate the speed, but that amounts to a lot of work. An easier way to solve this problem is to use energy. We can calculate the mechanical energy of the system pretty easily. We know that for the simple mass spring system, the mechanical energy is conserved and that it is equal to 1/2 Ka squared. K is given to us as 10, and we know the amplitude is 0.5 because remember, the amplitude is the maximum displacement, and this mass is pulled to a distance of 0.5 meters and then released. This mass will never go past 0.5 meters. It will simply oscillate between 0.5 meters and minus 0.5 meters. So it's pretty easy to determine that the amplitude of motion must be 0.5. From this formula, we can calculate the mechanical energy, and we find it to be 1.25 joules. We can also calculate the potential energy of the system. Remember that spring potential energy is given to you by 1/2 Kx squared. We know K and we know X. X is going to be 0.3 meters because that's the point we're interested in. So the mechanical energy at that moment in time is going to be 1.25. And the spring potential energy is going to be 0.45 joules. Now remember that mechanical energy is potential energy plus kinetic energy, which means kinetic energy can be expressed as mechanical energy minus spring potential energy. 1.25 minus 0.45 gives us the kinetic energy as 0.8 joules. Now this is important because we know that kinetic energy is equal to 1/2 mv squared. So we can say that 0.8 joules is equal to 1/2 mv squared. We know what the mass is. The mass is given to us as 2 kilograms up here. And so now we can use this equation here to quickly solve for velocity. And we find that the velocity or speed of the mass at coordinate x equals 0.3 is going to be approximately 0.894 meters per second. It's now time to learn about simple harmonic motion. Simple harmonic motion is motion that is described by this function here for any value of A, any value of omega, and any value of phi. Of course, you've already seen this function before. This is the function that describes the position of a mass in a mass spring system. What I'm saying here is that the motion of a simple mass spring system is an example of simple harmonic motion. As we will soon see, many other oscillating systems are described by essentially the same function. Usually the function describes the x-coordinate of some oscillating object, but it could also describe the y-coordinate, it could describe height, or even the angle of some system. Soon, for example, we'll learn about the motion of a pendulum, and we'll see that the same function essentially describes the angular position of a pendulum as it swings back and forth. Now, I've defined simple harmonic motion in terms of this function here, but it turns out that there are two equivalent definitions of simple harmonic motion. The motion of an object is described as simple harmonic motion whenever the net force acting on that object can be expressed as some constant times x. This was certainly true for the simple mass spring system. For the simple mass spring system, the net force acting on the mass was simply equal to the spring force, and the spring force, according to Mr. Hooke, was minus kx. You can see what we have here is some constant times x. Whenever you have a system where the net force on that system is proportional to x or is equal to some constant times x, you end up having simple harmonic motion. You end up having motion that can be described by this function. Another equivalent definition is to say that motion is simple harmonic motion whenever the object's potential energy is proportional to x squared. So whenever the potential energy is equal to some constant times x squared, then we have a situation where x can be described by this function. This was certainly the case for the simple mass spring system. For the simple mass spring system, the spring potential energy was equal to 1/2 kx squared. Again, you can see we have some constant times x squared, and therefore we must have simple harmonic motion. So in general, in studying engineering or studying nature, whenever you encounter a system in which the potential energy is given by this expression, or the net force is given by this expression, or the position is given by this expression, you can say you have simple harmonic motion. Simple harmonic motion arises in many contexts. Over the last few lectures, we've been concentrating on the horizontal mass spring system without any friction. We call this the simple mass spring system, but it turns out the same mathematics and the same ideas apply to a whole host of other oscillatory systems. For example, we will soon study the motion of a pendulum, and we will find that as a pendulum swings back and forth, its angular position can be described by pretty much the same function that describes the position of the block attached to a spring. In chapter 17 of our textbook, we'll discuss musical instruments, and we will find that the oscillations of a guitar string or the oscillations of air molecules inside a clarinet, for example, also obey simple harmonic motion. In other words, we will find that when you play a musical note on a clarinet, the air molecules inside oscillate back and forth very much in the same way that the block oscillates back and forth, or that the string guitars oscillate up and down very much in the same way that a pendulum might oscillate up and down. Under the right conditions, the swaying of a tall building in an earthquake can also be described as simple harmonic motion. The motion of electrons in an AC circuit that involves a resistor, an inductor, and a capacitor can also be described using the same function and the same mathematics that we've been using to describe the motion of a simple mass spring system. Now, we will not study all of these examples in this class. My point here simply is that simple harmonic motion is extremely important and that it's worth your time learning it thoroughly. Another reason why simple harmonic motion is important is because it is connected to uniform circular motion. Recall from your mechanics course that uniform circular motion is the motion of an object along a circular path with a constant speed. Simple harmonic motion, as we have just learned, is essentially the motion of an object along a straight line in an oscillatory or periodic fashion according to a cosine function or a sine function. It turns out these two types of motion are intimately connected. When it comes to uniform circular motion, what we're primarily interested in is the angular position of the object as a function of time, which is given by this formula. This formula essentially comes from angular kinematics, which is something that you should have learned in your mechanics course. Linear position in simple harmonic motion is given by this equation here, which we have now derived over several lectures. To see the connection between these two types of motion, imagine that you have a wheel, and imagine that this wheel is rotating with constant angular speed. Now imagine a point on the rim of this wheel. So imagine an object like maybe a knob or a handle that is somehow attached to the rim of the wheel, and it is going around with the wheel. We would say that the knob is executing uniform circular motion because it travels along a circular path with a constant speed. Now imagine that the wheel is oriented vertically and that there's a light source above, and that the light casts a shadow on a table below the wheel. So the wheel is simply rotating above a table, and what we can see on the table is the shadow of the knob. Notice as the knob itself moves along a circular path, its shadow simply moves along a straight line back and forth. It turns out the motion of the shadow can be described by this cosine function here. We could say that the shadow is executing simple harmonic motion while the object itself is executing uniform circular motion. Now, the terminology and the notation that we use in discussing these two types of motion is often different, but they are, of course, related. So when it comes to uniform circular motion, we often talk about the radius of the circle. When it comes to simple harmonic motion, we often talk about the amplitude of the motion. Those two things are equal. Obviously, if we had a wheel with a larger radius, then the amplitude of the motion of the shadow would also be larger. So it turns out the amplitude, which is the distance from equilibrium to, let's say, this position here on the extreme right, that amplitude is obviously equal to the radius of the wheel. When it comes to uniform circular motion, we often talk about angular velocity. And when it comes to simple harmonic motion, we often talk about angular frequency. These two quantities are equal to each other. They both essentially determine how quickly the motion is happening. If I increase the angular velocity of the wheel, the angular frequency of the shadow on the table would also increase. If you were to start this wheel rotating, you would have to decide what the initial angle of the knob is. We often denote that as theta sub 0 or theta sub I. And similarly, for simple harmonic motion, we have to decide where the motion begins. That's often controlled by phi. It turns out the initial angular position and the phase constant are also equal to each other. So although the equations look very similar, there are some important similarities between these two. And if you understand one type of motion, you can use that knowledge to understand the other type of motion. The connection between uniform circular motion and simple harmonic motion that we were just discussing is the basis of operation in both the steam engine and the internal combustion engine. So to give you a very simple model of what might be happening inside a steam engine or a gasoline engine in a car, consider a piston that is inside a cylinder. So we have a cylinder, inside it is a smaller cylinder that is free to move left and right. The piston is connected by a rod to a bracket, and the bracket is coupled to a knob, and the knob is attached to a wheel. Now imagine rotating the wheel somehow. As the wheel rotates, the knob rotates, and that causes the bracket to move left and right. As the bracket moves left and right, the piston will begin to move left and right inside the cylinder. So the uniform circular motion of the wheel will cause a simple harmonic motion of the piston. Of course, you can also reverse the order of operation. You could somehow force the piston to move left and right, and as it does so, it will force the wheel to execute uniform circular motion. This is exactly what happens inside a steam engine. Inside a steam engine, what we have is a cylinder that is filled with steam. That steam could be heated up or it could be cooled down. As it does so, it will begin to expand and contract. The expanding steam will push against the piston. As the piston moves outwards, it pushes against the wheel. So the simple harmonic motion of the piston drives the uniform circular motion of the wheel. Essentially, the same thing happens inside your car, assuming you drive an internal combustion engine car. If you drive a 4-cylinder car, you essentially have 4 pistons that are moving up and down in response to this expanding and contracting gas. The gas inside the cylinder is a volatile mixture of gasoline and air. This gas can be ignited. When it is ignited, it explodes. That explosion results in the rapid expansion of the gas, pushing the cylinder down. So the cylinder is executing simple harmonic motion up and down. It is coupled to a drivetrain, so the simple harmonic motion of these cylinders causes the flywheel to rotate, and the flywheel is then connected to other components which ultimately drive the wheels of the car. So as you can see, the connection between uniform circular motion and simple harmonic motion has many industrial and engineering applications, and it will be important for us to understand some of these applications. Let's end this lecture with a practice problem. A locomotive engine drives a piston. The piston's linear motion is described by this function here. The piston is coupled to a wheel with a radius of 0.4 meters. How fast does the train move? So I'm describing for you the type of thing that I've been showing you. What we have is a piston, and this piston is being driven by a steam engine. Now, we don't know exactly the detailed operation of a steam engine, but I can tell you that as the steam engine operates, the piston basically executes simple harmonic motion, left and right, let's say, in this animation, according to this function here. You can see that in this function, the amplitude is 0.4, the angular frequency is 3, and the phase constant, or phi, is simply 0 in this particular case. This piston is connected to the wheel of a train, let's say, and this particular wheel has a radius of 0.4. So the simple harmonic motion of the piston drives the uniform circular motion of the wheel, and then of course the wheel will cause the train to move forward. I want to know how fast does the train move, what's the speed of the train in response to this uniform circular motion. Now notice that I'm essentially telling you that the angular frequency of the piston is 3, or 3 radians per second. That fact is simply observed by looking at this number here. The number that multiplies time is omega. Remember that in general we describe simple harmonic motion using this function here, a cosine omega t plus phi. So by comparing this function here to the function that's given to you, you can quickly determine that omega must be 3. Now, on the previous slide, I explained to you that the angular frequency of simple harmonic motion is equal to the angular velocity of uniform circular motion. In fact, that's essentially why we use the same letter, omega, for both of those quantities. So now I know that the angular velocity of the wheel must be 3 radians per second. Now, I'm not really interested in the angular velocity of the wheel. I'm interested in the linear velocity of the wheel. Here you have to imagine that this wheel is kind of rotating on the ground and that it is moving forward. I want to know what that linear velocity is. At this point, it helps to remember some relationships between angular and linear quantities. Hopefully you remember from your mechanics course that linear velocity is equal to the radius times angular velocity. We know what the radius is, which is 0.4. We know the angular velocity is 3 radians per second. And so the linear velocity of the wheel and the train to which it is attached will be 1.2 meters per second. And that is the end of this lecture. Thank you for your attention.